U2 from Applied Math and Physics, and then a number of 2 or 3 third years that have spoken to me. So we're going to all try and go together. So what this is a collection of information that I made about the most relativistic pulsar. It's 0737, 3039. So the name tells you the coordinates in the sky where the pulsar is. So we label our pulsars by their actual location in the sky, whereas we label gravitational wave events by time. Okay, it's simply the identifying version, or time and date, or when they arrived. So this pulsar story, it's in the southern hemisphere, and you can see from basically the minus 30 part 39, it's exactly overhead of us. So it is an ideal observational candidate for Meerkat. And it's also nice because you have the longest, if you have something transiting right overhead, you have the longest possible observation time for the pulsar. And let's just go on. Its story was, it was discovered in April 2003 by Parkes in a high latitude survey, and it had a 2.5 hour orbit. So there are 2 things that characterize a pulsar, at least initially. The one is that it's basically a lighthouse beam that is rotating. Okay, in other words, you have this beam of radio waves that, if you're fortunate enough, it crosses your field of view and you see like a little blip in your observation time. So it literally looks like a heartbeat every time the beam crosses your field of view. And the second period that's usually characteristic of these systems is, if they are in a binary, it's the orbital period. Okay, so that's the rotational frequency is usually, in this case, is milliseconds, and the orbital period is 2 hours. And in the school that I think Matthew and them are going to have, they said they're going to analyze a 2-hour pulsar. So I don't know if it's this one or something else that's very, very close. So it's a very relativistic pulsar we're going to be looking at there. And so because this is the one I know the best, that I thought I would give you a concrete view at all the things we can actually do with it. So the first pulsar that was ever discovered we call a Hulse-Taylor pulsar. We were also very fortunate there in that it was a relativistic pulsar. So we used the Hulse-Taylor pulsar before we had gravitational waves. It was the direct observation of gravitational waves. It was the first pulsar we actually could measure the fact that the orbit starts out here, emits gravitational waves, and then it shrinks. And because we haven't done gravitational waves in the course yet, it's simply view of it as just like a charge gives off electromagnetic waves, and that carries away energy and angular momentum. So the gravitational waves, if you have a mass moving around each other, they also give off waves, and that carries away energy and angular momentum. And the result is there's a total conservation of energy, and that means that the orbit actually shrinks. As the energy is lost, when the gravitational waves carries it away, the orbit shrinks. And in fact, every gravitating body does that. Okay, so for this particular thing, you can also see the orbit shrinking, and in fact, it is shrinking about by 7 millimeters a day. The Earth's orbit, if you just look at the Earth-Sun system, it is also losing, it also gives off gravitational waves, and it also in principle shrinks. It's just very, very small. So if you actually work out the calculation for the number of gravitational waves the Earth emits as it goes around the Sun, the result will result in an orbital shrinkage of a fraction of the width of an atom every year. Okay, so it's just so tiny we don't see it. And the other things at play, like the solar wind that blows off particles from the Sun, actually pushes the Earth away. So these two kind of balance out, and it's roughly the same scale. So we don't see it for the Earth-Sun system, but mathematically it's still there. Okay, so this thing is shrinking 7 millimeters a day, and we've been observing it. So all my information that I'm giving here is dated in the sense that I literally looked at this last 5 years ago. So everything is like before 2017 that is my cutoff for where I got it. A lot of stuff has happened since then, but it's maybe good to understand the base behind it as well. So it shrinks over the 13 years from 2003 to 2003 plus 13. So this is 2017. It literally shrunk 35.4 meters. Okay. Its currently orbital velocity is 1 million kilometers per hour. It is separated, the two bodies are separated by about 900,000 kilometers. And it is the 8 light seconds. It takes 3 seconds to travel from there to there. Okay, so to give you an idea for the Earth-Sun system, it takes 8 minutes for light from the sun to get to us. Okay, so there's 3 light second separation, and at the rate that it's going to emit gravitational waves, it's going to actually crash into each other and coalesce in 85 million years. Okay, so there's no chance of it crashing, but it is an inevitable in-spiral to collision. And we've actually seen some of those with LIGO. Okay, so it was in 2017, I haven't checked again, the only known double pulsar. And by double pulsar, I mean you have one pulsar that has a beam that rotates that you can record, and you have a second one. And what makes the system remarkable is, for a while at least, we saw both beams. Then mathematically, the number of parameters you can fix, because you're timing not 1 but 2, is tremendously more. And this is why it is so good for making tests. Okay. And so there are 2 pulsars. The one is pulsar A. Okay. It has a spin period of milliseconds and was discovered first, 23 milliseconds. The second one is pulsar B. It has a much slower spin period of 2.7 seconds. So what that tells us basically is that most probably pulsar A was formed first. And usually pulsars are not born with spinning so very rapidly. So what usually happens is you would have one pulsar being born, you would have another pulsar not yet born. And then in the process where it goes from a star that radiates energy to being a pulsar, it usually puffs some excess gas into what they call a Roche lobe. And then what occurs then is that there's a mass transfer from the gas around the second pulsar. It goes through this Roche lobe and it spirals in around the one that formed first. And this occurs while the second pulsar is forming. And when that happens, this gas that spirals in keeps hitting the surface of the pulsar that was formed first, making it spin faster and faster and faster. So usually these things weren't born with a spin rate. That was due to the fact of the companion that was giving gas off that hit it and made it spin faster and faster. So it basically pushed it up to 23 milliseconds. Okay? And the guy that's really good at this and looking at the formation mechanism is Piran and Shavi. They basically look at formation mechanisms of pulsars. So the one thing, every single statement I've made here at the last slide, there's all the papers I used, if anybody wants to go back and check where they are. And most of them I have. So if you can't get them immediately off the archive, I actually do have them. And so I'll actually post these. I'll make us a pulsar website, and I'll actually put this up if you want to go back and look at it or use it for a project or something. Okay, so another thing, proper motion refers to the system as such moving relative to us. Okay, so we have the binary system going around each other like that. Typically, when we describe the pulsar, we go into a coordinate system that's associated with a binary. But the possibility exists that that coordinate system can also move relative to us. In other words, you have your binary moving like that, and we haven't detected that. And why that is useful, there's several things in this pulsar that's just amazingly nice for analyzing it. Why that is useful is that if there's no proper motion, what sometimes happens if you have proper motion is that you have your pulsar moving and there's gas and stuff in between that can obscure the radio waves and distort them that come to you. You don't have to worry about that. Okay, so if there's no proper motion, there's literally one line of sight, and that tends to be pretty clean. So it just makes our observations, give us greater confidence in observations, and makes the errors when you start fitting the models smaller. A very super cool thing is that we're actually looking at the system edge on, okay? And so what that means is, so for all you on that side, your pulsar is basically stuck within this disk, moving around like that, and you're looking at it roughly with 3 degrees, okay? And that, what makes that useful is that you can actually see the one pulsar come towards you and the other one move away. So you can actually clearly see the Doppler effect of the pulsar redshift and blue shifting if it comes towards you. You also, in this case, can actually see the one pulsar eclipse the other one, which is highly, highly rare, which is how we know it's not more than 3 degrees, because these pulsars are tiny. They're like, their radius is about 10 kilometers, right? So we have the mass of the sun squashed into 10 kilometers. So you only have a little 10 kilometer thing here. You have 700 kilometers, 900,000 kilometers between them. So they have to be lined up really, really well so for you to obliterate the signal from this one. It is an amazing coincidence that this is actually what happened with the system. And this is why everybody's so excited about it, and me too. So what actually happens is the eclipse occurs for 30 seconds. Okay, and if you look at the numbers, it actually means that the eclipse is being formed not by a 10 kilometer sized object, but rather a bigger object. What's forming the eclipse is not the pulsars like hard. So, I mean, a pulsar is literally a neutron star, which means that it's made out of matter. Unlike most things on Earth, it's more akin to a giant neutral bunch of neutrons. So it's extremely dense. So what you're actually seeing during the eclipse, it's not the pulsar itself, because that's tiny, occluding the light that's coming. What's actually happening is the light is hitting the electromagnetic magnetosphere around the pulsar, which is actually a bigger thing than the pulsar itself. Okay, and that was actually a confusion for a large amount of time, because initially they said, oh, it's 30 seconds, that means the pulsar is huge, or whatever is huge, but it's not the pulsar is huge, it's the signals that are experiencing interference from the magnetosphere, much as our DSTV in a storm starts quitting because there are things in the atmosphere that obstruct the radio waves. Okay, so it's edge on. Its eclipses occur for 30 seconds, and A's beam hits B's magnetosphere, and it is an A's beam is what they call an orthogonal rotator, okay, which is to me something I don't understand how it got to be that way. So an orthogonal rotator is you have your spin axis up here, and then you have your beams literally coming for A. You have the spin axis normal to the plane or the orbital plane, so it's spinning around this. This is for A, and the beams are coming out like this one, stuck in the plane itself, and that's important for several reasons. So we've been doing parallel transport in or at least starting to introduce it in the tensor analysis class, how you take a vector, put it on a path in a manifold. And the one thing I said was, if you transport a vector around a curve in the manifold, and the manifold is curved, the vector won't come back and be the same. Okay? That's true for almost all vectors, but depending on your curvature and depending on your basically on the curvature of the manifold and on your path, it is still possible for a vector to go around and come back and be the same. Okay, and the case for the orthogonal rotator is one such. So if you have an orthogonal rotator in a Schwarzschild, say in this case space-time, and you transport it right around, then it's not going to change its orientation. Okay, however, if it's at an angle, it is. Okay, so this one is going to remain, its spin axis is not going to change so much. Yes?
Is that why they say we can see beings slide in the next 5 years? Because it's...
Yeah, good question. We think so. Okay. And that's part of the thing that it's a very nice thing to actually do with Meerkat, because it has such high sensitivities to actually go and look for what you're seeing. They haven't seen it yet, or they claim they haven't seen it yet. I'm sure there will be somebody watching for it. There might be ways of doing it better. So that's something that will be incredibly exciting. But you're jumping ahead of my story. Right. Anyway, so that's it. So A is an orthogonal rotator. It's the one that's basically the carrier signal. Right. Just to give you context, in 2017, and I do these things because I want to see where we are, there were 2,500 known pulsars everywhere, slightly more maybe, that had ever been discovered. Now there are a lot more due to FAST and due to Meerkat itself. 300 of those were in binaries. Okay. But these weren't binaries with other neutron stars. Usually what happens is you form a pulsar while the other one is still like a star. Then when the pulsar once a pulsar is formed, the other one goes to the end of it, basically dies. The pulsar is in some sense a dead star, it no longer burns. The other ones, when they then live out their life, the one forms first, and when they die, they throw off a whole bunch of dead stuff, and that tends to go onto the pulsar and suck away from their mass. So typically, you have binaries where one's a pulsar and the other one is a white dwarf, and the pulsar has taken a lot of the white dwarf's mass. Okay, it's very, very unusual to form neutron-star binaries. So if you have a neutron-star binary, it means that the other pulsar is heavy enough to form a neutron star. Okay. So of the 300 binaries, only 12 are double neutron stars. And the way we know it's a double neutron star is often by simply being able to get the mass. We know the first one's a neutron star because it's a pulsar. White dwarfs don't make beams. We know the next one is a neutron star because we can look at the orbit, and from the orbit, we're fitting the orbit, we can get the mass. And if the mass is more than a Chandrasekhar limit, which is a certain limit, it cannot be anything else. It cannot be a white dwarf, so it has to be a neutron star. Typically, it's like between 0.9 absolute minimum, more like 1.2 and 3. Those are the masses solar masses. Those are the masses that the neutron stars actually have. So 12 of those are neutron stars. And only one of those, in 2018, this is when this plot was made, is actually a double pulsar. So when we plot pulsars, what we typically do is we make a graph of the spin period of the pulsar we're looking at versus how that period is changing. Okay? Often that tells you things about the age of the pulsar, and it's also very easily observationally to do that, right? You can basically take a Fourier transform of the data. That's very roughly what the analysis is. And then you get the spike happening at the spin period, and then you'll see if you do the Fourier transform at different times, that spike is actually going to move, and how it moves is on the second axis. So if you look at all known pulsars, these are the dots. The binary systems, or the 12 neutron star systems, are over here, okay? And the double pulsar system actually has 2 spots, right? Here's the one, which is pulsar A, which has a very, very short period, and there's this other one, which is pulsar B, which has a much longer period, okay, a 2-second period. So just in relation to how we know pulsars, it's kind of useful to sometimes at least know where these guys are. And this is basically also a standard plot people make whenever they want to discuss their pulsars, because it tells you about the formation mechanisms, and it tells you about the age of the pulsar. Right. Now, let's look at a little bit more of how we describe a pulsar. So The description for the pulsar's dynamics is a form of approximating GR that they call the post-Newtonian expansion. So post-Newtonian basically stands for Newtonian, referring to if there was no GR, you would have a double system and your system would be on an elliptic orbit, right? And that's what I proved to you guys in the booster class for last year. Was exactly how the pulses are, like the Newtonian system I actually solved in full. If you want to take a look at it, there's a booster website, and I actually give the analysis there. So it basically derives why, if you're working just in Newton, you're always on an ellipse. So one thing that you need to take away when you transition from Newton to gravity, or from Newton to GR, many people say, oh, wow, and then they want to throw away all of Newtonian gravity. And that's not true. There's a very clear transition, a very smooth transition from Newtonian gravity to GR. In fact, when your gravitational field is not strong, it's literally that GR is a perturbation on Newtonian gravity. And so what people did initially is they wanted to solve the Einstein equations in a place where they actually knew the answer. And so they were basically perturbing off of Newtonian gravity and looking for how Einstein's theory would change Newtonian gravity. And that's quite a highly developed scheme, but they basically worked out the first corrections of Newtonian gravity in this post-Newtonian theory. And the way they versed it is, if you describe any ellipse, okay, what you have to do is you have to, or any two-body system, you have to put your coordinate system at the origin, your center of mass, okay? Then you have to, one of the results, if you're just working in Newtonian gravity, is that your orbit remains in a single three-dimensional plane. Then you have to describe that plane. So it's basically choosing the origin of your coordinate system, choosing the orientation of your plane, okay? The origin of a coordinate system is 3 numbers. The orientation of your plane is another 3 numbers, okay? And then you have to describe your orbit. So to describe an ellipse, it's basically the eccentricity of your ellipse that measures how spherical or how elliptical it is. It's the major direction into which the biggest loop of your ellipse is. And then it's where on the ellipse you are, okay? So those numbers that I've just summarized are your orbital parameters. It's what the minimum amount of numbers that you need to describe a system. And what happens is if you have Newtonian gravity, all those things are constants. Okay. They are constants if, as in our case, there's no proper motion. In other words, if the binary system center of mass is at a fixed point. For now, let's just assume, and it's true for the system, that if it were a Newtonian system, they're all constants. Okay, so here I've gone to basically give you the normal type of structure that people historically developed. So, for example, typically you have a reference direction. That's where you are watching from. Okay, so that's a thing that's fixed for you. Then you have the origin, which is where the origin of the coordinate system is. Then you're going to have a coordinate system that's associated with a plane of the orbit, but you're going to have an angle between the reference direction, namely the way you view it, and the actual plane where the orbit is. So in our case, that's also very simple because this orbit is lying almost 3 degrees from the reference angle. Okay. Then you're basically going to have where the maximum of the orbit or the orbit of the ellipse is, and that's basically, they call that, what do they call it? Basically, it's this point, argument of periapsis or something. And then you're going to have where your body is moving on the orbit, okay, and that's usually given by an angle on the orbit. And then you're also going to have, that's about it, right? So you're basically going to have numbers that describe your orbit, your Newtonian orbit. So what your post-Newtonian theory does is it simply says, if I'm in GR, and they've done it not only for GR, but a whole bunch of other theories as well. They said, if I'm in GR predicts that these parameters will change in a certain way, okay? And they will change basically dependent on the general mass of the system. So you have like six or more Newtonian parameters. They all have a predicted change depending on the fact that you have GR, and that change depends just on, I think, 2 parameters itself. Okay, so what we then do is we watch the data, and we actually can measure how each of these, by fitting the spikes that come through, or the pulses that come through, we can measure how these parameters are changing, okay? And that, the way you do that measurement, is a timing model. Is what we call a timing model, and that's what they're going to do, or hopefully help show us how they fit it in their particular case with the Meerkat data. Okay, but whenever you work with data, you can only get a certain amount of parameters in the fit. And in fact, that's what many people a mistake people often make is you need a certain amount of data to say something. So the people that have been doing pulsar analysis are very, very careful with this. And it's actually one of the places where you get the cleanest statistics. So for example, the Hulse-Taylor pulsar that was discovered first, with the data they have, they can only fix 3 post-Keplerian or post-Keplerian. So Kepler was given the name of the ellipse, basically. 3 parameters that tell you how the ellipse is varying. Okay. There's another binary pulsar that you can also fit 3 parameters. There's one that you can fit 4, and J0737, you could fit 5 in 2017. Subsequently, they fitted a few more. Okay, so these are the parameters. The most important parameters that you get is basically how the orbit is shrinking, which is directly due to gravitational waves, and how the ellipse is actually moving. Okay, so one of the predictions, the first way relativity was checked, was the fact that was already an observation that was there before it was verified, was the fact that Mercury's orbit is an ellipse, but the periastron, the point at which the ellipse gets the biggest bulge, it tends to move. Okay, and it's tiny for Mercury. It's like 10 to the minus 4 degrees per year. Okay, for this particular pulsar 0737, the periastron advances, that's basically how this maximum is moving, is 17 degrees a year. So it's huge. Okay, and so you can actually, when you plot the orbit, you can see this typical advance, and the differential equation that actually governs the thing in Schwarzschild is very, very simple. And most of you that have done my dynamical systems class have actually treated the dynamical system that describes it. Okay, so that's the one thing that you can actually check, and it's kind of nice to see it happen. So I think we are going to look at how the orbit shrinks due to gravitational radiation rather than this periastron advance, but they would have actually fitted this if they wanted to fit the orbital shrinkage as well. Okay. So it's one of the most beautiful demonstrations of what GR actually does to an orbit, and how you can tell the difference between a space-time that is basically flat in the case of Newton, as opposed to one that's strongly curved for these systems, or relatively strongly curved for these systems. Up until we measured gravitational waves, this was the strongest probe of a curved space-time. Right, so now if you have a pulsar, you can learn more, okay? And the other way you learn more is by looking at the pulse profile. And what I mean by a pulse profile is, if you have this pulsar over here, you're sitting at where you guys are, and you have the beam coming across. My first picture showed that it just looked like a headlight of a car over there, right? It's like this car beam that comes across. There's nothing that says it has to be like that. This beam is formed by a whole bunch of electrons that are spiraling out along the magnetic axis. I don't fully understand how orthogonal rotators actually work, right? They must have had their magnetic field at 90 degrees to the spin. And I don't know how it actually happened to be that way, but it is. Okay, so you have your beam, you have electrons spiraling around your magnetic field, they give off light, synchrotron radiation, and that you see as you come across. But it need not be a car light, right? Something could happen. You could have some funny material in there, or you could have something, internal structure of your pulsar that changes the magnetic field, and then the light you give it out can have a different structure. In fact, you could have like one very strong beam in the middle, and you could have a cone around it. And the way you see it is as this beam comes across, when you actually measure the light, you're first going to get the light from the edge of the beam. Then as you sweep across, you're going to get light from the center part, or radio waves, and then you're going to finally see the end. And the way that picture looks like is what we call a pulse profile. So the way we measure a pulse profile is we simply have this stream of pulses that come at us. An individual pulse, maybe you cannot really see. If you look at the data, it's just noise. It's more than 99.998% noise. It literally looks like gray noise if you look at the data. So what people do is they know the pulse period. So you chop the data in pulse periods, and then you put everything on top of each other, okay? And then the noise on average goes to 0, and the pulse, the shape of the pulse comes out. And if you do that, you get a profile that looks like this. Okay, so this is what they call the average pulse profile of the thing that rotates rapidly. So that is simply, if you take, I don't know how many observations, but literally thousands of observations, you chop them up, shifted them all, that the pulses coincide, and then you take the average picture, the noise goes down, there it is, and then this thing pops out. And then people study what this thing does and try and infer something about the beam that's coming across. And so what you can see over here is there's definitely a asymmetry. It looks like the image starts, or the intensity increases slowly over here if it's rotating that way, and then you have a little hump over there, then you have most of the radiation, and then it falls off very rapidly. I'm not an expert in knowing how to describe this. There are people that did that, and Marissa did a little bit. A little bit of this, and I think Isabella also studied that, so you'll meet them both at the thing, and you can ask them those questions. So this is what P1 looks like. This is the profile of, oh no, wait. Both these profiles are for J0737A. Okay, so this is the millisecond pulsar. So here what you can basically see is you're going to have the two beams, right? So the one beam is going to come across. That's the first hump. It's going to go around, and then the next one's going to come across. So you're actually seeing that the beam facing the one way is different from the beam facing the other way.
But why?
I don't know. I didn't dig into that.
You will think it will be the same.
No. I mean, if there's a mountain range on your pulsar, then, and it happens to be where that beam originates, you can have a mountain range on the one side. I don't think pulsars have mountain ranges, because gravitation is so strong it's going to basically flatten any mountain range. But if there's something weird in the structure of the neutron star on the one side, it can support a beam. Or if somehow the other pulsar if there's a moon around your pulsar, or something got stuck there, it's going to change the shape. It's actually very interesting to look at all the possible pulse profiles you get, and I think that's another sort of field of study. There are people that have made catalogs of that, and to try and understand that. There's a lot still to be discovered there. So yeah, the base assumption that they made usually is that it's the symmetrical, and this is pretty close to symmetrical, but it is not always. It's not. Physics happens, right? And then you refine your model and you see what you can learn for that. And it's good to be alert to those type of things.
I think this is a stupid question, but we said like it orbits in 23 milliseconds.
Yeah.
Is that half an orbit or the entire orbit?
It rotates in 23 milliseconds.
Sorry, is it a full rotation or half rotation?
It's a full rotation because this is the full profile. Okay, so you have the one coming in a little bit later, you have the other one coming in. And you'll see that here it's sort of, this is 1 gives you the full orbit. So you have sort of 0.5 between the two, which is nice. So at least the two beams point in different directions. There are pulsars that actually don't do that and we don't understand them.
And is the y-axis on that graph basically light intensity, or what as we measure?
Yes, sorry. It's radio intensity. Aggregate radio intensity, I think, over a certain frequency range of Parkes, most probably, who made the observation. Okay. Another fact is that it's 0.009, the eccentricity. So one feature of gravitational radiation as well is it carries energy and angular momentum, and as it does that, it tends to circularize an orbit. So generally, if you have an orbit that is emitting gravitational radiation, it's going to become circular and circular. And that's why with the SAG-A calculation, the thing that actually resulted in the mathematical result was the fact that the orbit was, I assume the orbit was circular, but it's a good justification if somebody ever asks you, is that all orbits in a strongly gravitating body tends to circularize when they carry away gravitational radiation. So it wasn't just it was actually a very well motivated initial calculation. So the eccentricity is 0.009. That's relatively low, but it's still there.
So, sorry.
Yeah.
I don't know if I'm jumping ahead.
No, go for it.
But this is, like we said, an orthogonal rotator. If it's not an orthogonal rotator, is the pulse profile going to change?
Yes, it's going to disappear. Yes, exactly. And they have looked at, so pulsar, so this is just A. Pulsar B is not an orthogonal rotator. Its pulse profile has changed and it's disappeared. And this is what you said, that it's going to come back. But let's get there. Okay, so we've done A. This is B. It's 0.2 seconds. So this, if you basically do the Fourier transform, they initially missed. So initially what they do is they take the observation for thousands of patches over the sky. They do Fourier transform them and they look at frequencies that stick out. Then they have ways of culling things that are most probably not pulsars. And then they look for these things. Initially, what's interesting is that they didn't notice this low frequency. Okay, so initially, the initial discovery, they said there was just one pulsar. It was discovered in April 2003, and the second pulsar was discovered only October of that year, right? Because for various reasons, it is a strange pulsar, and its emission is strange as well. And so the reason it was only discovered later is for some reason, it only emits at 2 15-minute periods when it's in its orbit. So its emission is strange in the sense that the emission we see only gets emitted when it goes here and then when it goes there. Okay, so this is the line of sight. This is what the direction is to Earth. And for some reason, it only emits light when at certain parts of the orbit. Okay, I don't know if there's a full model for why it does that. But it is a very distinctive pulse at 0.7 milliseconds, and all its other behavior is consistent with the fact that it's a pulsar, but it's only pulsing, its pulsing mechanism only switches on at certain parts during its orbit. It's one of the mysteries that are there.
Is it possible that it switches on away from Earth and we can't see it?
Yeah. But you must remember the orbit, the relative position of the orbit also changes. So it's going around each other. It's like got eccentricity, and then that moves. So eventually we will see it, simply because the structure is in some sense rotating and Earth is remaining the same. So it's eventually going to. So I don't think that's the reason, but it's just a feature. The reason they missed it first was maybe when the first observation was there. It was in one of its not emitting periods. And then the second observation, they actually saw it and then they knew where to look for it. But there's been a number of observations, and it's clear that it only does it in these two parts of the orbit relative to its origin. Okay, so it tends to switch on, go pulse, 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 like you see over here, and it emits pulsars in bursts, and they can actually be seen individually. So we know it's a real pulsar. It's not just some figment, because that's one of the problems with detecting these things. And they can see that there's weak emission elsewhere. Where once they knew what to look for, they could actually see the other places other places in the orbit. And what they could also do is they could see the profile of the pulse effect changes. Okay, so you're going to have, depending on where in your orbit you are, the pulse profile is going to be different. So there's clearly something happening with that beam that's a lot less stable than the other pulsar, but they've measured that. And they can measure it accurately enough to actually time it. Like these pulses do only come every 2.7 seconds. And the moment you can time the second pulsar, you can measure the individual masses. So if you look at the analysis, there's certain parameters that enter into the model fit in a certain way. And you need to be able to measure certain things to be able to actually fix the masses. So generally, if you can time one pulsar, you can fix the average mass of the system, but not the individual masses of the pulsars. If you can time two, you can get the individual masses. And this is what makes the system so powerful, because you have independent ways of measuring the same thing. And so, yeah, so this is what those pulses basically look like in various frequency bands. So they're there. It's a definite pulsar. It's just behaving very strangely, and we don't fully understand how it's behaving, why it's behaving that way.
So, sorry, I just want to make sure I understand. So the B pulsar is on the red curve, the red circle.
Yeah, the B pulsar is on the red circle.
I want to say doesn't emit, and then when it reaches those areas, it starts to emit at 2.7 seconds.
So it emits softly, weakly, at other places as well. Okay, but over here it sometimes really switches on, and you can see the amplitude go up.
So it continues to pulse at 2.7 seconds, but it's not a strong pulse except for in those two regions.
Yes, and you can connect. So what the model does, it has a pulse. It says 2.7 seconds, and so there's many. Right, it's 2 hours for it to go around, 2.4 hours. So 2.7 seconds in many hours, you can actually work out how many pulses there are. And the amazing thing is it switches on here, pulses around, and then when it gets to this side, it's exactly like clockwork. So it's not as if the mechanism has switched off. It's just not seen. And then it like kicks in at exactly the right time. So this comes the spin precession, but I think I can, let me say it because you asked the question. Okay. So this is the spin precession, okay? So based on the orientation of the spin, okay, and the actual system, the spin precession for B is 75 years, okay? So it's basically the wobble that the spin axis is going to do, okay? The spin precession for A you can also work out, but because it's an orthogonal rotator, it's going to do that, right? It's not going to change that much. So its beam is actually not going to disappear. Whereas the B, its spin axis is not aligned normal to the plane. It's literally, its spin axis is going to change quite dramatically over 75 years. And the orbital precession, just to give you an idea, remember I said the orbit was changing, it had that periastron advance, and that was 17 degrees a year, and that basically means in 21 years it's going to precess completely. Okay, so that's a relative thing. And so what happens with a spin precession is you can actually work it out, and here's a little bit of how it's done. This won't make sense to you until we've actually done how you parallel transport a vector around the thing. So that's how they derived it. But it's basically very similar. So what people did here is they wrote it in terms of, if you view a spinning top, you take a top and you spin it, then it's got a spin axis, and once it gets off vertical, if it's vertical, it's exactly the same picture in fact. If it's vertical, the spin axis, it's not going to wobble too much. But if it goes down there, if it's at an angle to the vertical, it's going to start doing this. Okay, it's exactly the same reason why A doesn't move that much and B is going to have this wobble. Okay, and so whenever we do this type of thing, we actually cast the GR to look exactly like the spin axis. So this is basically looking at how the thing is going to wobble, and the feature that sets the time scale is this constant that you make up out of these various things. You can actually derive that. So the rate at which the precession occurs, in some sense the wobble, these 75 years, is made up initially of this formula where m was the mass of the one object, m2 is the mass of the other one, and big M is the total mass of the system, and these are the orbital parameters, and this is the period of the orbit. So you actually have a very nice formula in GR that predicts how the thing is going to spin, and we can actually derive that, and we might do that depending on the time that goes. And so this is just an example of your, once again, a pulse profile. A B's profile, I haven't got here now, is more complicated than A's. And some people say that it's one of the models for it is this idea where you have a central beam emitting with a cusp around it, and your line of sight tends to cut the beam over there. I don't know the extent to which I believe that. It's just a model that tries to describe what B actually looks like. And if you have that, then you can see your profile is basically going to be, you sort of cut the first one, it gets darker, and then you have a little hump here at the second one, and then you cut the second. So depending on how strong the emission is in these things, you will see different things. One advantage if your beam is precessing, right, your pulse profile is going to change. And so if your beam moves through your line of sight, this profile is going to change, and you can imagine you cutting at a different area. So you're actually going to be able to build up a bigger picture of the pulse profile, provided the pulse profile doesn't change. And there's no guarantee of that with B, okay? With A, we know it's so stable for so long that it looks as if it's not changing, and it looks as if it's not moving itself. So I think I'm actually going to stop there now. Questions otherwise?
Does the Doppler effect affect the image of the pulse pulse profile?
A little bit. It depends on which pulse profile you're looking at. So